E si scopre che a bordo della Stazione Spaziale Internazionale il tempo scorre in modo diverso rispetto alla Terra e vogliamo misurarlo con una precisione di una parte su milione. Quale sarebbe un fattore? Da 10 a 20 volte meglio dei limiti attuali?
Benvenuti, io sono Massimo Polidoro e state per ascoltare il Gomitolo Atomico, il mio video podcast che va online ogni martedì sul mio canale YouTube. Se volete vedere questa puntata, oltre ad ascoltarla, la trovate su YouTube insieme a tutte le altre. E ora, buon ascolto! Che cosa significa davvero misurare il tempo? È qualcosa che noi attraversiamo, che ci scorre addosso, ma è anche un fenomeno che noi cerchiamo di catturare, no? Comprendere, tradurre in numeri. Oggi in questa puntata speciale del Gomitolo Atomico, siamo in trasferta ancora a Berna, incontriamo uno scienziato che ha dedicato la sua vita a spingersi fino al limite della precisione. Christophe Salomon, fisico dell'École Normale Supérieure di Parigi, è tra i pionieri della ricerca sugli atomi ultrafreddi, particelle portate a temperature così basse da rivelare il comportamento più intimo della materia. Insieme ad André Clairon ha ideato i primi orologi a fontana di atomi freddi, strumenti così sensibili da ridefinire gli standard internazionali del tempo e rendere tangibile lo spazio-tempo di Einstein. Il suo lavoro ha spostato più in là i confini della metrologia e, con essi, la nostra capacità di mettere alla prova le leggi fondamentali della fisica. Quest'anno il Premio Internazionale Balzan ha riconosciuto il suo contributo come uno dei più innovativi nel campo della fisica contemporanea. Ogni anno, lo sapete, il Premio Balzan mette in luce ricercatori, pensatori, studiosi che hanno aperto nuove vie alla conoscenza. Figure che con la loro curiosità, il loro rigore hanno trasformato il modo in cui noi guardiamo il mondo. In questa serie abbiamo davvero la possibilità di incontrarli uno a uno, attraversando discipline diversissime, dalla filosofia politica alla medicina, dalla storia dell'arte alla fisica, per scoprire come nasce davvero una grande idea. Sono conversazioni in inglese e sono tutte sottotitolate, lo sapete, ma ne vale veramente la pena perché sono incontri che ci aiutano a spostare lo sguardo e lasciano domande più che risposte. Prima di parlare con il professor Salomon, ho voluto chiedere a Massimo Inguscio, professore emerito di fisica della materia presso l'Università Campus Biomedico di Roma, presidente emerito del Consiglio Nazionale delle Ricerche e membro del Comitato Generale del Premio Balzan, di aiutarci a capire perché questa ricerca ha cambiato il modo di misurare e forse anche di pensare il tempo. Allora, grazie professore Inguscio. Ci spiega chi è Christophe Salomon e qual è il cuore del suo contributo?
Christophe è stato uno dei protagonisti, diciamo, di questo incipit, di come cioè si può prendere un gas di atomi che normalmente si muove come le molecole, diciamo, in questa stanza a velocità di centinaia di metri al secondo, e invece lo si può rallentare questo moto fino a diventare di pochi millimetri o centimetri al secondo. È stato il primo forse che ha capito come in pratica questa potesse essere la chiave di volta per misurare il tempo. Lui in particolare poi propone di realizzare e realizza uno strumento che si chiama fontana atomica. Cioè, una volta che uno, usando la luce di un laser, rallenta questi atomi, fa un palloccolo, una nuvoletta di atomi che invece di muoversi, ripeto, a centinaia di chilometri al secondo, si muovono di pochi decine di millimetri, come dire, al secondo, e quindi li intrappola, li localizza. Dopodiché da sotto dà una spinta, sempre con un laser, e questi atomi che fanno? Questo palloccolo va in alto, e poi, come noi sperimentiamo quando lanciamo in alto un sasso, il sasso ci torna addosso e noi ci scansiamo, e così questi atomi vanno in alto e come in una fontana ricadono in giù. allora tutto il tempo di salita e di discesa diventa un tempo in cui io misuro questa transizione. Realizza la fontana, e questa fontana al cesio è adesso distribuita in decine laboratori di metrologia al mondo. Noi in Italia lo abbiamo, la fontana, al nostro istituto di metrologia INRIM, che si trova a Torino, poi ce n'è ovviamente uno negli Stati Uniti, uno in Giappone, insomma dovunque, perché questi campioni, che sono quindi distribuiti su tutta la Terra, su tutto il nostro pianeta, che si confrontano continuamente con dei link che viaggiano tramite satellite e diciamo definiscono il tempo che noi chiamiamo universale, quello che è uguale, come dire, per tutti. Il progresso della scienza e della tecnologia e tutto, sta tutto nelle sorprese. Quando uno ha uno strumento più potente, è chiaro che il mondo, in senso lato, viene visto con un'accuratezza maggiore, viene visto meglio nella sua complessità. Ora l'economia è fatta da cambi in borsa che avvengono con una risoluzione di 1/1000 di secondo, oppure da internet che viaggia alla velocità della luce. Sono le sorprese che ci inducono ad andare avanti e vanno capite. Quindi questa ricerca premia l'abilità di Christophe Salomon di essere uno scienziato molto rigoroso, ma anche, come dire, visionario, tant'è che queste cose saranno utilissime anche perché, come sapete, il Premio Balzan viene dato allo scienziato, ma anche per metà a un progetto che lui presenta. E non c'è nessun progetto che meglio rappresenti questa cosa della Balzan, perché adesso, avendo questo orologio di Christophe Salomon sulla stazione orbitale, che produrrà un sacco di dati, si collegherà con tanti posti al mondo, diciamo, Germania, Francia, ovviamente, Stati Uniti e via discorrendo, produrrà tanti di quei dati che necessiterà di studi molto approfonditi per capire quali sono le correlazioni, i legami, per vedere come le cose tornano. E questo verrà fatto grazie a tanti giovani appassionati, come dire, di questo mondo, che potranno, come dire, lavorare, essere assunti in questa bellissima impresa grazie appunto alla Fondazione Balzan, e quindi diciamo, è davvero un bel esempio.
E ora siamo pronti per ascoltare Christophe Salomon, che incontriamo qui a Berna in occasione della cerimonia di premiazione, per capire che cosa si impara a osservare il tempo con una tale pazienza e precisione. Nella nostra conversazione, lo vedrete, parleremo di come rallentare gli atomi aiuti a vedere più a fondo nell'universo, di come la misura del tempo sia diventata una forma di esplorazione e di che cosa significhi passare la vita intera a inseguire l'esattezza. Professor Salomon, it's a pleasure to have you here with us. So, my first question for you is, does time exist?
We are in Bern.
We are in Bern.
We are in Bern. Bern is a place where Einstein developed its theory of special relativity between 1903 and 1905, and he showed that actually there is no universal time like everyone experiences it in its own life. Time is different in different gravitational potential, so time is different on the Earth, on a satellite, or in a distant star. So this was a true revolution, actually, because after Newton, it was thought that the time was flowing uniformly, was the same for everyone on the planet or even in the universe, but this is not true. And so this was a big conceptual, intellectual change with major impact. Einstein was not alone, actually. This was following some Minkowski, Poincaré, Lorentz, physicists who had thought about this time. And so this was special relativity, which was only half of the discussion on the time. The second part was general relativity, showing how matter is coupled to space-time, to space like where we live here, and time. And this makes a unique block. You cannot dissociate space and time. It's a unique block, which is governed by the equation of general relativity, but it's a bit too specialized to talk about that.
But, so what is time for you?
Time is what a clock measures. Following Einstein, time is what a clock measures. And this clock is associated to yours. You have one clock, I have another clock, and you can synchronize clocks. You see, you can ask the question, does your time is similar to my time? How does it differ from your time from my time? And this we can measure. I think people have many meaning for time. You have a time for your life. Your heartbeat, is really a regular clock. You see, you have a life duration. Some animals live a couple of days. Some others live 100 years. So you have also a biological time. You have also a time in music. In music, you have silence, you have a rhythm, which are modulation, time modulation of the musical language, music's phrase. So you see, time is experienced very differently by very different people. And I think they all have a common point, which is a sequence of events, and but they are all valid, I think.
Absolutely. You started in engineering, right?
Yes, I did.
And then moved into a high-resolution laser spectroscopy.
Indeed, yeah.
So in simple terms, what is laser spectroscopy and what drew you to it?
So my engineering school actually was a bit a deception for me because the physics course were not good, except one teacher. Okay. And so I liked physics because I had excellent teachers at the preparatory school before entering engineering school. And so I was a bit frustrated, and then I decided to go on at the university after my engineering school to go one more year, which would be Master 1, degree now, where I had absolutely excellent teachers, which were really connected to modern research, laser physics, nonlinear optics, and so there I got really excited by this field of research, which was light and matter, light-matter interaction, how you excite atoms, molecules, how you can measure things in the atmosphere. So I was drawn to laser spectroscopy, maybe not really by the subject, but by people, by my PhD advisor, Christian Bordet, who was really a very motivating mentor in a sense. So he was excited, explaining me the beauty of a very new technique of nonlinear physics, nonlinear optics, where you could push the spectroscopy, 5 orders of magnitude beyond the existing one by some nonlinear techniques, sub-Doppler spectroscopy, how it was called. So this is why I joined this group. And then I remember, then after a year or so, I said, okay, but why is this important? You see, why is it to make spectroscopy of molecules in the infrared with infrared lasers, which were difficult to run and so forth? Why is it that important? So I had to go to conferences, be confronted to other people working in the field to see how this effort in laser physics, nonlinear optics, would be part of a bigger target or bigger subject. Then I understood more and more what it was to be a researcher in that domain.
La spettroscopia. Se ancora a casa avete dei fornelli a gas, provate a buttare un po' di sale da cucina e viene fuori una fiammata gialla. Se mettete in un tubo del neon, che è un gas nobile, quello è rosso. se vedete dei fuochi d'artificio, vedete blu, verde. Ecco, queste sono tutte sostanze, tutta la natura, diciamo, è fatta intanto di atomi, come noi, e sono tutte sostanze che hanno dei colori caratteristici. Cioè la fiammata gialla sul fornello è il sodio, il sale da cucina è fatto da cloruro di sodio, quindi la spettroscopia da sempre è stata la scienza di capire, come dire, cosa c'è, no? A fare l'analisi spettroscopica e dire qui c'è il tal minerale, il tal gas e via discorrendo. La spettroscopia è una scienza antichissima e consente di vedere dal colore, di capire, come dire, che cosa c'è. Può bastare pensare un po' ai colori dell'arcobaleno, che sono un po', come dire, più sfumati, no? Se si passa dall'uno all'altro gradualmente, ai colori di una bolla di sapone, che intanto sono cangianti, ma se riflettete un pochettino bene, quando uno vede il flash verde oppure dopo quello rosso, eccetera, sono dei colori che sono quasi più metallici, perché sono ben definiti, più definiti. Ora il laser può farli ancora più precisi, e quindi è una sorgente con cui si fanno cose molto precise. Allora, cos'è il raffreddamento laser? Il raffreddamento laser è che se io ho un gas, in questa stanza ho molecole più che atomi, ma se c'è un gas di atomi, pensate a quello che volete, e gli viene mandato il colore giusto, quest'atomo, diciamo, lo assorbe. Se invece non glielo mandate giusto, non lo assorbe. Però il giochetto è molto interessante, perché se voi lo assorbe, calma, e poi lo riemette, no? E poi, come la luce gialla del sodio sul fornello eccitato, poi lo riemette in tutti i modi. Però se io non gli mando proprio il colore giusto, ma un pochettino spostato verso energie più minori, allora l'atomo lo assorbe comunque, anche se con minore efficienza, però poi lo riemette da tutte le parti, diciamo, a tutte le frequenze. Quindi a botte di assorbire un po' meno e riemettere di più, che cosa fa? L'energia si deve conservare, quindi questo povero atomo deve rallentare. Questo è il raffreddamento laser.
And then you began cooling atoms with lasers, trying to push them towards absolute zero, right? So why do that, and how should we picture a temperature so low that our everyday idea of cold no longer applies?
No, your everyday idea of cold does apply. Does apply. It's the same temperature than the room temperature here is 25 degrees or so. And we express it in absolute temperature because there is a zero of temperature where everything is at rest, except for quantum effects, which we are not going to describe. But quasi-zero motion means zero temperature, means perfect order. This is why you get crystals, for instance, because when you cool water, you end up with a crystal of water, and this is because nature becomes ordered. The disorder of molecules flying in all directions gets reduced, and sometimes nature tells us that this state of matter, ice, has less energy than all the molecules running around. And so laser cooling is exactly doing the same thing for atoms. And if this distribution of particles has an average speed, which is zero on average, but has an average quadratic mean, is reduced by a factor 100, then the temperature is reduced by a factor 10 to the 4. So we go from room temperature, typical room temperature, to 100 microkelvin. And then we had a big surprise in this research that the temperature that was reached was even below the theoretical temperature. And so this was a very exciting moment. So it's one of these famous cases where, nature is much richer than what you can imagine. Oh, yes. And this has opened the way to measuring time better, because These very low temperatures are essential to make an atomic fountain. If the temperature is very low, it makes a fountain that goes straight and go back down very, very straight as well. Like the Geneva fountain, it shoots above the lake and with very little spread transversely. And the atoms do exactly the same. You shoot the atoms up and they expand, and when they fall down, they make a bigger sphere. But at 1 microkelvin, this sphere has just very little expanded.
Together with André Clairon, you built the first cold atom fountain, then clocks, devices so precise they reshaped how we measure time. Can you explain how they work in simple terms, of course?
Yeah, you start with, you have a vacuum chamber because those atoms are very fragile. At 1 microkelvin above absolute zero, you cannot touch a table. You cannot touch a window because if you touch it, the atom gets warm, gets to the temperature of the table, you see? So, first of all, everything happens in vacuum. And the forces that we exert on the atoms are with the light. And then with light, we launch the atom upwards, and they will do what we call a parabolic flight. They go like a fountain, up and down. And to make a clock, you apply a field, electromagnetic field, that will excite the atoms. Or more precisely, that will make the atom cycle between two energy levels, the ground state of the atom and an excited state. And the atom, when excited, can cycle up and down like this for a very long time. In particular, the time it takes for the atom to have a first interaction on the way up, make a round trip, second interaction on the way down. And it is a beautiful technique that was invented by Norman Ramsay, who got him the Nobel Prize, by the way, for that invention, is that the atom cycles like this, and the field cycle also at a speed which is very close to the other one. And then you have an interference pattern. An interference pattern, like interference in the window when you have a film of water, you see fringes appearing, you measure whether the atoms are excited or not. And the key point of the fountain is that this interference effect depends only on the height that the atom goes above the cavity, and more precisely on the time that the atom spends above the cavity. And the interference fringe is narrower and narrower when this time is longer and longer. And this is where you gain for the clock operation, because you make a very narrow interference fringe, and then you lock your oscillator, that was your quartz, you lock it on this very narrow structure. And you can imagine that if you force your oscillator to be stuck at the top of the resonance, if the resonance is very broad, it's no good. If the resonance is very sharp, it's much better. And so this is what makes use of cold atoms, because the resonance is much sharper with cold atoms than with a thermal beam.
Let's try like a mental experiment, an imagination experiment, like Einstein did. What would happen if we turned off all the clocks in the world? Would time still happen?
That would be big mess.
Well, definitely.
Big mess for aviation.
Oh, for everybody, yes.
Big mess for cars, for transport, for all sorts of synchronization. You will have dead people on the road, in the train, synchronization. So it would be a big mess. Yeah. And by the way, I can mention that the satellite time from GPS or in the European system Galileo is fragile. We know that it can be attacked or blurred. And this is what is happening in the Ukrainian war, actually. It's very easy to scramble the GPS signal. It's so weak because it's emitted by satellite far away that by a very small 30 euro noise generator, you can scramble GPS signals over some area, a small area or bigger area. And so here we should mention that this high precision time is somewhat fragile, the time that comes from satellite. Of course, the armies, they know that since a long time and develop other means to compare time, and there are other means to compare time. But I think no time would be a big mess.
You know that science often emerges from accidents, unexpected events that you were not planning for. Was there ever a near failure or a surprising result that changed the direction of your work?
Well, there were many near failures and many failures as well. I can mention many of those. One of them is that when we did the fountain clock, my collaborator André Clairon had prepared the what we call a frequency chain, going from the quartz oscillator, which is at 10 megahertz, to make it to 10 gigahertz. So we have a multiplication chain. So he had worked, he was a genius in electronics, and he was a great collaborator, and so I missed him. But, and so it happens that during the transportation, maybe by a shock or something, the quartz was not where it was supposed to be. So we have spent days and nights and days and nights searching for the cesium signal, because you have to find the resonance very precisely. And in a fountain, the resonance is very narrow. And so the quartz was here, and the cesium resonance was there. So we could not find anything, for 2 weeks or so, and get tired looking at zero signal. Until we had the idea, okay, there must be something wrong with this source. Let's borrow another clock. So we borrowed a clock from people doing geodesy, and they had a portable rubidium clock. And we saw that the quartz was off by a large amount. So we retuned it, and then the next day, we did not get the signal the next day. We knew we were at the right position, but we had forgotten one thing, which was to apply a guiding magnetic field. And so we tried again a couple of days and nights, and then we said, let's apply a magnetic field in the vertical direction. And then the signal appeared. Wow. And this was a big joy, after months of efforts, to really a great joy to see the signal. And the signal was good, actually, very quickly, rather good, actually.
Today, these clocks are sensitive enough to probe things like dark matter or tiny shifts in the constants of nature. Do you feel clocks are becoming instruments to explore the most fundamental laws of reality?
Oh, yes, I think so, because we did experiments along these lines. And this was a really fundamental question, like raised by Paul Dirac a long time ago. Well, we know we have a cesium atom or a hydrogen atom. What is telling you that a billion years ago, or at the early stage of the universe, this cesium atom or hydrogen atom would be the same? Can we prove that? Can we test this hypothesis of universality of elementary particle? And the answer is, as of today, of course, we cannot probe atoms way in the back unless we do astrophysics. So we look at lines emitted long time ago, lines emitted by stars, far back, in time. And this light comes to us today, and we can compare the emission line a billion years ago to the line that we measure in the lab today. And whether they're shifted or not, we can make measurements of this hypothesis. And so what we have done and what people are still doing now is to check also today, let's say when I say today, it's over the last 10 years, for instance, whether one of the most fundamental constants of nature, the fine structure constant, which characterizes the strength of electromagnetic interaction, why an atom has this size, this mass, this number of electrons, So it's a fundamental coupling constant of electromagnetism, dimensionless quantity. Is it changing with time or not? And the answer is it is not changing with time at a rate of a couple of parts in 10 to the 19th. So it is very stable today. Does not mean it was not different in the past, but it cannot be vastly different. And you can also interpret this kind of data as if you had seen a modulation of the fine structure constant, you can view it also as the existence of dark matter, light dark matter. So those are two aspects of the same type of measurements.
What is really exciting now for you? What is the idea on the frontier of your research? Do you already know what you will use, for example, your Balzan Prize?
We want to make a fundamental test of the Einstein's theory. That's on the agenda. By comparing a space clock to a set of ground clocks with an ultra-stable link, because a clock on its own has no use. You have to compare it to something else. I give you a clock. What you do, you read something with your eye. And so you compare it to your human clock, right? So, or you count your beat heart and you compare your heartbeat to your clock. That's what every physician is doing, yes? And so you have to compare clocks into a different situation. And it turns out that on board the International Space Station, time flows differently than on Earth, and we want to measure this to 1 part per million, so, which would be a factor 10 to 20 better than the existing limits. So then there are two choices. Either you find Einstein is wrong, then you have to make sure that you are not fooling ourselves with systematic effects. That will be an interesting game. Or you find that you are in agreement with general relativity to a better level. But theoreticians today know that GR, general relativity, and quantum mechanics are not unified. And so there must be some more general theory. And they do predict either new particles or new fields, that would interact with matter, not very strongly, because otherwise we would see it already. But this is why this kind of test, actually of fundamental laws, is important in the spirit of physicists, because of course if you discover new law or violation of the existing law, it's very exciting because you have to find a new particle, a new field, and so that is one of the motivations. And another one, which is more practical, is to use the Einstein effect, assume it's correct at some level, let's say a part per million, and then you can do Earth geodesy with a totally different means than what is done today by geodesy people. People use satellites, ranging, and so forth to measure the Earth's potential and Earth's potential deformation, for instance, with the melting of the polar cap. And so with the Einstein effect, you can return the argument and I say I can measure very precisely the potential difference between here and there. So it's an application in Earth science. So it's less fundamental, but still very important to know if this potential is raising up as a function of time or going down with respect to that one. So that's one of the major directions where clocks are heading, with the hope, perhaps, in the future to be able to not predict, but give indication of potential earthquake if you see anomalies as a function of time. So the numbers are a bit challenging, but the clocks are making a huge progress, but perhaps clock in the future will help to, I would not say, not prevent, but warn, perhaps, for earthquake. But these kind of studies have to be made and tested.
Wow, yes. I have one small and last question for you. I need to show you something. Okay, so this is a mystery box. It's a box, cardboard box, which is sealed, it's closed, we don't know what's inside. But let's imagine that inside this box there is the answer to some question, to some mystery, to something that you've been wondering about for all your life, maybe. What answer would you like to find in such a box?
I would like to find a theory that unifies gravity and quantum mechanics.
Absolutely, well.
So that's a physicist answer, right?
And so let's suppose that you really do have this answer inside this box. Would you prefer to open it and know it right away, or maybe find the answer yourself through your research?
I think I would open it because I'm very curious.
You would like to know right away?
Yeah, I would like to know right away, because this is one of the big questions that is on the market today, because we see anomalies in astrophysics. We see dark matter, dark energy, and there are a huge effort to try to nail down what is responsible for that, and any idea on this would be a great advance.
Absolutely.
So, mystery box.
Thank you, Professor Salomon, for having
Thank you for your nice interview.
It's been a pleasure.